The atmosphere does not announce itself. It does not issue warnings or give press conferences. It simply loads, building energy over days and weeks, accumulating the ingredients for violence in the invisible layers above the Earth, until the moment when it releases everything at once. In early June 1984, two separate but eerily similar atmospheric patterns are loading simultaneously on opposite sides of the planet. In the central United States, a low-pressure system is tracking eastward across the Great Plains, dragging Gulf moisture north and colliding it with dry air spilling down from the Rockies. Above it, the jet stream is screaming at nearly 100 knots, generating the wind shear that turns ordinary thunderstorms into rotating supercells. The Storm Prediction Center in Kansas City is watching the setup develop with the particular alertness of people who have seen this before. Simultaneously, 5,000 miles to the east, a different but structurally related story is unfolding. Over Eastern Europe, a powerful trough is amplifying and tracking northeast. Warm, moist air from the Black Sea is being drawn northward by southerly winds, pushing dew points of 18 to 20 degrees Celsius as far north as Moscow. Moisture values that belong to July, not the first week of June. The 500 millibar geopotential height over the region on June 8th and 9th will later be measured at 2.7 standard deviations below normal. In meteorological terms, this is not a routine summer storm. This is an outlier. This is the kind of atmospheric event that happens once in a generation. These two patterns are not the same system. They share no direct atmospheric connection. The trough over Eastern Europe has its own origins, its own life cycle, its own moisture source. But they are the same kind of event, a deep, anomalous trough generating the precise combination of instability, shear, and lift that the atmosphere requires to produce violent, long-track tornadoes. In the first week of June 1984, this combination occurs on two continents within 48 hours of each other. What follows is one of the most remarkable coincidences in the recorded history of severe weather, and a window into questions about planetary-scale atmospheric patterns that science is still working to fully answer. June 7, 1984. Afternoon, the central United States. A dry line has settled across eastern Nebraska like a boundary drawn in the sky. To the west, the air is bone dry. To the east, Gulf moisture streams north in a river of energy. By mid-afternoon, the first storms are firing along this boundary. The first tornado of what will become a two-day multi-state outbreak touches down near Mobile, Iowa. An F1, relatively minor, tracking through farmland. 7 miles, no deaths. An opening act that gives little indication of what is building behind it. By late afternoon, 5 separate supercells are mature and rotating across the Great Plains. They're rotating updrafts visible on radar, their anvil tops spreading at 50,000 feet. The long-track F4 that forms over northern Missouri in the early evening hours is a different order of event entirely. It tracks more than 130 miles from Missouri into Iowa, a family of tornadoes produced by the same supercell, moving for over 2 hours across the heartland, killing 3 people, including one in Missouri's Harrison County. Farms that have stood for generations are erased. The storm generates baseball-sized hail and straight-line winds extending miles from the main circulation. This is not a tornado, it is a siege. As evening becomes night, the outbreak should begin to wind down. Tornadoes feed on solar heating, the sun's energy destabilizing the lower atmosphere, fueling the updrafts that drive supercell rotation. When the sun sets, the fuel should diminish. Most outbreaks do weaken after dark. On the night of June 7th, the low-level jet stream does not allow this. The low-level jet is a ribbon of fast-moving air in the lower atmosphere, around 3,000 feet above the surface, that acts as a conveyor belt, pumping Gulf moisture northward at speeds of 50 to 60 miles per hour through the night. When it activates strongly, it can keep the atmosphere unstable and the storms rotating long after sunset. On the night of June 7, 1984, it activates. The storms don't weaken. They move into Wisconsin. The village of Barneveld sits in a valley in Iowa County, Wisconsin, surrounded by rolling hills and the prominent Blue Mound to the east. Population 584. For more than a century, the people of Barneveld have carried a belief that those hills protect them, that the terrain deflects tornadoes, that the valley is a refuge. It is a belief common to communities across the Midwest, a piece of local folklore that feels like knowledge because it has never been tested. On the night of June 7th, most of Barneveld is asleep. It is after midnight. There is no internet, no cell phone, no way for a warning to reach a person in their bedroom, unless a television is on or a weather radio is programmed and activated. Television stations in 1984 signed off after the 10 p.m. news. The tornado watch that the National Weather Service had issued for the region had been in place for hours, but the funnel cloud would touch down outside the village limits and be on top of the town in less than a minute. There was, as the meteorologist who covered it afterwards said, simply no time left. Dan Wohl was the Barneveld school superintendent. On the evening of June 7th, he had attended a school board meeting to discuss his contract as a new hire. He went to bed that night not knowing that the meeting was the last ordinary thing he would do for a very long time. Marianne Myers lived in a duplex in Barneveld with her mother-in-law's home adjoining hers. At 12:50 a.m. on June 8th, her bay windows began to shake. The wind blew the bathroom door shut on her wrist. The clock on the wall read 12:50 a.m. When she pushed through the bathroom into her mother-in-law's side of the duplex, it was gone. In the seconds it had taken her to cross a bathroom, the other half of her building had been swept away. She looked out into her front yard and saw a boat from down the block wrapped around one of her trees. "That's when I started to realize," she said later, "this was no small event." At 12:41 a.m., a tornado had touched down 5 miles southwest of Barneveld. It intensified as it moved northeast. By the time it reached the village, it was an EF5, the highest classification on the Fujita scale, awarded not on the basis of measured wind speed, but on the basis of what the tornado did to the structures in its path. What it did to the structures in Barneveld earned that rating beyond any scientific dispute. The tornado was 400 yards wide and moving at over 60 miles per hour. Lightning strikes had cut power to the village minutes before it arrived. The tornado siren at the fire station, the only warning system Barneveld had, never sounded. In 170 of Barneveld's 225 buildings, the night of June 8, 1984 was the last night they stood. 17 of 18 businesses were destroyed. All 3 churches were demolished. The Congregational United Church of Christ, the Lutheran Church, the Roman Catholic Church, the post office, the library, the fire station itself, 93 homes completely destroyed, 64 others severely damaged. Paperwork from the village was carried 135 miles northeast. The National Weather Service recorded lightning flashing more than 200 times per minute during the storm, a strobe effect that Terry Kelly, the chief meteorologist at WKOW television, saw from his home and immediately understood as wrong. He and his photographer rented a helicopter and were the first media to reach Barneveld at dawn. "I could easily see that there was very little left," Kelly said. "I mean, everything was flattened." 9 people died in Barneveld. 3 of them were children. A third of the village, 197 people, were injured. One thing remained standing through everything. The water tower, damaged but not toppled, rising above the flattened town like a monument to what had been there. The village adopted a motto in the days that followed: "We're not giving up, we're going on." Dan Wohl, who would spend the following months fighting with insurance adjusters, arguing with contractors, and pushing the community toward rebuilding through a winter that came too soon, later said a more accurate motto would have been something harder: "Whatever it takes." The Barneveld tornado was the worst single event of the American outbreak, but it was not the only one. 7 tornadoes carved paths of destruction across southern Wisconsin through the early hours of June 8th. Additional violent tornadoes struck Iowa and Minnesota on June 7th. 13 people died across the 2-day outbreak, with 9 of those deaths in Barneveld alone. 322 people were injured across 3 states. The meteorological signature of the outbreak was later analyzed in detail. The Barneveld tornado was the most recent F5 or EF5 tornado to touch down at night in American recorded history. It joined a rare and grim roster: the Blackwell and Udall tornadoes from the 1955 Great Plains outbreak, the downtown Lubbock tornado of 1970, the Tanner and Gwynn tornadoes from the 1974 super outbreak. Nocturnal violent tornadoes are not common. When they occur, the death tolls are disproportionate because warnings cannot reach sleeping people the way they can reach people who are awake and watching the sky. Barneveld was also the second F5 in Wisconsin's recorded history. The first had occurred in Colfax in 1958, 26 years earlier. The fact that two F5 tornadoes had now occurred in a state not traditionally considered part of Tornado Alley was a data point that meteorologists filed away, not yet sure what to make of it. On the other side of the planet, as Wisconsin was beginning the long work of counting its dead and clearing its debris, the atmosphere over Eastern Europe was doing something that almost no one in the Western world would learn about for years. The Soviet Union in 1984 did not publicize its natural disasters. The Cold War information environment meant that a catastrophic tornado outbreak north of Moscow in the textile city of Ivanovo, 254 kilometers northeast of the capital, would be reported in local newspapers with careful understatement, its death toll suppressed by authorities who had no tradition of acknowledging domestic catastrophe to their own citizens, let alone to the world. What Western meteorologists knew in June 1984 was almost nothing. What they would eventually piece together from eyewitness accounts, satellite imagery, and the work of Russian researchers writing in the years after Glasnost is a picture of an outbreak that rivals anything in European meteorological history. On June 8th, a 500 millibar trough over Eastern Europe began rapidly amplifying. A surface low formed over Romania and tracked north-northeast at 60 kilometers per hour, deepening by 9 millibars over 12 hours, the meteorological signature of an explosively intensifying storm system. Warm, moist air from the Black Sea was being drawn northward along the warm sector ahead of an advancing cold front, carrying dew points of 18 to 20 degrees Celsius far north of where they belonged in early June. The jet stream overhead was carrying winds of more than 100 knots. The ingredients were in place. On the morning of June 9th, the first tornadoes touched down southwest of Moscow. By mid-morning, the outbreak was producing multiple violent supercells tracking north-northeast at speeds exceeding 80 kilometers per hour. At least 8 tornadic thunderstorms produced between 8 and 13 tornadoes across the Ivanovo and Yaroslavl regions, an area of more than 400,000 square kilometers. The outbreak would later be classified as the third deadliest tornado outbreak in European history. At approximately 11:50 a.m. Moscow time, the tornado that history would call the Ivanovo-Lunyovo tornado struck the city of Ivanovo. Ivanovo was not a small village. It was an industrial city of nearly 500,000 people, Russia's historic textile capital, known since the 19th century as the Russian Manchester. The tornado that entered the city was 1,130 meters wide at its maximum extent. Witnesses who survived it described the funnel as shining from within, lit by its own electrical activity, glowing like the inside of a furnace. Smaller vortices detached from the main funnel and spun around it before being reabsorbed. The sound was unlike anything anyone had heard before. The damage was consistent with F4 intensity, the retrospective rating assigned by Western meteorologists analyzing the documented evidence decades later, since the Soviet Union did not use the Fujita scale. A 350-ton operating crane was knocked over. A 50,000-kilogram water tank was thrown 200 meters. Asphalt was stripped from highway surfaces and scattered. Steel-reinforced buildings lost their roofs. Wooden structures were obliterated. The tornado's path through Ivanovo and the surrounding villages and forests covered between 80 and 160 kilometers, one of the longest documented tornado tracks in European history. The second major tornado of the outbreak struck the city of Kostroma and may have been of equal or greater intensity. Russian researchers in the 1980s debated whether the Ivanovo and Kostroma tornadoes were the same continuous vortex or separate events from the same storm. Modern satellite analysis of forest damage patterns, published decades later, has helped clarify some of the track characteristics, but the question of the outbreak's full scope remains partially open, a consequence of the information suppression that defined the Soviet response. The hailstones that fell across the affected region during the outbreak weighed up to 1 kilogram. A single hailstone at that weight, falling at terminal velocity, carries the energy of a brick dropped from a significant height. 1 kilogram hailstones are among the heaviest ever confirmed anywhere in the world. The official Soviet death toll for the June 9th outbreak was 69 people. Local newspapers reported the event primarily as a hailstorm. The tornadoes themselves were barely mentioned. The scale of the destruction, the number of villages damaged or destroyed, the human toll, all of it was managed carefully through state media in keeping with Cold War-era policies that treated domestic disasters as information to be controlled rather than communicated. Western diplomats in Moscow estimated the actual death toll at approximately 400. This figure appears in the peer-reviewed meteorological literature, specifically in the 2012 study by Finch and Bikos published in the Electronic Journal of Severe Storms Meteorology, which represents the most thorough Western scientific analysis of the outbreak. The discrepancy between 69 and 400 is not a rounding error. It reflects what happens when a government decides that the image of stability is more important than the count of the dead. The people of Ivanovo knew what had happened. They had seen it, survived it, lost neighbors and family members to it. But for years, the full story existed only in the memories of those who had been there, and in the carefully worded accounts of Russian researchers who published what they could within the constraints of what the state would permit. It was not until the glasnost period of the late 1980s that more complete accounts began to surface. And it was not until satellite imagery from the outbreak was analyzed by modern researchers, matching forest damage patterns to storm tracks, reconstructing tornado paths that ground surveys had never fully documented, that the scientific record began to approach something like completeness. In Ivanovo today, the tornado of June 9, 1984, is remembered. The city has memorials. The survivors are elderly now, but their accounts were preserved and the scholarly work continues. In 2025, researchers presented new WRF model simulations of the outbreak at the European Conference on Severe Storms in Utrecht. 41 years later, scientists are still working to understand exactly what the atmosphere did over Western Russia on that June morning. The question that hangs over both outbreaks is the one the script in your original version stated as fact, and that the research requires us to handle more carefully. Were these events connected? The honest answer is probably not directly, but possibly in ways we do not yet fully understand. The American outbreak was driven by a low-pressure system that formed over the central United States and drew Gulf moisture northward. The Soviet outbreak was driven by a separate trough that amplified over Eastern Europe and drew Black Sea moisture northward. These are different moisture sources, different pressure systems, different storm tracks. The peer-reviewed meteorological literature does not establish a direct causal link between the two outbreaks. What the literature does establish is that both outbreaks occurred within a period of anomalous large-scale atmospheric circulation over the northern hemisphere. In both cases, deep upper-level troughs produced 500 millibar heights far below normal. The American trough generating its outbreak on June 7th. The European trough generating its outbreak on June 9th. Both drew anomalous moisture northward from warm ocean surfaces. Both produced the kind of atmospheric instability and wind shear that generates violent tornadoes in regions that rarely see them. Whether these patterns share a common origin in the planetary scale flow of the atmosphere, in the behavior of the jet stream as a global system, in the ocean temperatures that influence large-scale circulation, in the kinds of hemispheric scale patterns that modern climate science is only beginning to characterize, is a question that remains genuinely open. Researchers studying the relationship between climate variability and tornado outbreaks have documented that some large-scale atmospheric patterns, known as teleconnections, can simultaneously favor severe weather in widely separated regions. Whether June 1984 represents one such event is not established. It is a compelling hypothesis. It may be more than that. What can be said with confidence is this. In 48 hours in early June 1984, the atmosphere produced two of the most violent tornado outbreaks in the recorded history of their respective continents. One killed 13 people in the American Midwest, including 9 in a sleeping village that never heard its siren. The other killed, officially 69, possibly 400, people in a Soviet industrial city whose government chose to suppress the true scale of what had happened. Both outbreaks shared the same fundamental atmospheric architecture: deep troughs, anomalous moisture, extreme wind shear, populations in regions that had rarely or never experienced tornadoes of such violence. In Barneveld, the rebuilding took years. The town that emerged was physically newer than the town that had stood before June 8th. which meant that in a strange way the destruction had produced what destruction sometimes produces: better construction, stricter codes, more resistant structures. The water tower that had survived everything was repaired and remained. A memorial park was established to honor the 9 who died. In 2024, on the 40th anniversary, village trustee Mike Peterson was still raising funds to restore the memorial, still working to keep the memory alive in a town where the physical evidence of the disaster had long since been replaced by newer buildings and grown trees. The tornado itself changed American meteorology in specific ways. Dr. Ted Fujita, who had developed the scale that now bore his name, came to Barneveld to study the damage personally. The absence of a hook echo on radar, the classic signature meteorologists use to identify rotating supercells, meant that forecasters watching the storm had not known a tornado was forming. Barneveld contributed to the push for Doppler radar, which can detect the rotation inside a thunderstorm before a funnel cloud is visible. The National Doppler Radar Network that was eventually built across the United States was partly motivated by events like Barneveld, by the recognition that the existing radar technology could not see inside storms with sufficient precision to warn people in time. In Ivanovo, the outbreak became a turning point in Soviet severe weather research, though the political constraints of the era meant the lessons were absorbed slowly and incompletely. After Glasnost, Russian meteorologists began publishing more openly about the event and about tornado climatology in the Soviet Union more broadly. The work of researchers like Snitkovsky in the late 1980s and the satellite-based studies that followed decades later have gradually built a picture of a country that experiences more tornadoes than its citizens or its government had ever acknowledged. 40 years on, the June 1984 outbreaks sit in the meteorological record as two of the most important tornado events of the 20th century. Not because of their death tolls, which are significant but not the largest in history, and not because of their geographic scope, but because of what they revealed about where violent tornadoes can occur and what the atmosphere is capable of producing outside the places and seasons where such things are expected. Barneveld was not in Tornado Alley. Ivanovo was not in any tornado alley at all. Wisconsin in June and Western Russia in June are not the kinds of places or times that populate the mental model most people carry of where tornado disasters happen. They carry that mental model because it is largely correct, and partly wrong. Tornadoes do occur most frequently in the American Great Plains in spring, but the atmosphere is not constrained by human geography or human calendars. When the ingredients align, they align. In June 1984, they aligned twice. The question of whether the two alignments were coincidence or whether they reflect something in the large-scale behavior of the planetary atmosphere that science has not yet fully characterized is not a closed question. Climate researchers studying the relationship between ocean temperatures, jet stream behavior, and tornado outbreaks have documented patterns that suggest the global atmosphere can simultaneously favor violent weather in widely separated regions. Whether June 1984 is an example of this is still being investigated. The 2025 European Conference on Severe Storms included new modeling of the Ivanovo outbreak. The work continues. Marianne Myers saw a boat wrapped around her tree and understood that something had changed permanently. Dan Wall argued with insurance adjusters and contractors for a year and rebuilt a school and a community. Terry Kelly flew over the wreckage in a helicopter at dawn and saw that almost nothing was left. The residents of Ivanovo watched a tornado shining from within like a boiler pass through their city and took their dead from the rubble in a country that would not officially count them all. What these people experienced is the ground-level reality of what atmospheric science studies in the abstract. The trough, the shear, the instability, the moisture. These are the terms in which the atmosphere describes itself. In June 1984, it described itself in the same terms on two continents within 2 days, and the people who happened to be living in its path paid the price for conditions they had no way of anticipating because their communities had never been in that path before. The atmosphere does not know where Tornado Alley ends.